Great. Well, thanks everybody for joining. Welcome to the fourth installment of the RISC-V Israel Meetup group. And as we're facing this current situation, this is again a virtual event. So I'm pleased you're all able to make it. I hope you're all safe. And as we were saying earlier there in the warm-up, I hope you've all got a good cup of coffee or something ready as we go through this evening's presentations. So I'm just going to give a brief introduction here, and then we're going to kick off with some presentations. So my name's Kevin McDermott. I'm with Imperas, and I'm the guest host for this afternoon's evening session. Our first presentation will be from Syntacore, talking about their RISC-V IP solutions, both open source and commercial cores. We have Kate here today. She can wave. You may have heard earlier, we have Larry Lapides from Imperas talking about the most important part of RISC-V, which is the design verification. And then later on, we'll have Zvonimir join in from Western Digital. He's involved with some DAC activities, I believe, right here early in California. So he'll be calling in with the latest updates for CHIPS Alliance and the SweRV cores. And then for those of you that joined a little bit earlier, I just wanted to highlight a couple of other events that will be coming up here shortly. On September 3rd, the Global RISC-V Forum will be a worldwide global event looking at about 18 hours of coverage across all activities around the world involved with RISC-V. So please look out for the schedule and join if you can. And then looking further ahead out to December, the traditional RISC-V Summit will be taking place, and we're looking forward to either perhaps a full in-person event or possibly a hybrid or a virtual event. We'll have to see how things shape up. But coming back here to the agenda, I think that was enough of a preamble. And just to highlight here at the end of today's presentations, all the panelists will be available for Q&A. And in the true Meetup style, we'd like you to please ask any questions. There's a chat box, and you can post anything there through the presentations, and we'll gather them up there at the end. So I think that's enough of a preamble. And so hopefully, Kate, you're ready to start sharing.
Okay, so let's start. Hello, everyone. My name is Kate, and I am hardware design engineer at Syntacore. And today I will introduce you to my company, Syntacore, and our CPU IP solutions and services. First of all, a few words about the company. Syntacore is an IP company. We are founding members of the RISC-V Foundation, and we're among the initial several companies which were there right from the start. The company was founded in 2015, and it is headquartered in Cyprus, and has more than 15 employees in 2 R&D offices in St. Petersburg and in Moscow. Most of them are engineers. We have local representatives in EMEA and APAC region. In EMEA, we are presented by Red Tree Solution. Some of you may be familiar with. More especially, here in Israel, you can contact Zohar, who I believe is in a call with us today. The core team has extensive relevant experience of more than 15 years in R&D of major semiconductor companies. The areas of expertise include low power and high performance embedded cores and IP, ASIC technologies, reconfigurable architectures, as well as architecture exploration, workload characterization, and compiler technologies. So what do we offer? First and foremost, we develop and license RISC-V compatible CPU IP. We've been doing this for more than 5 years, and our initial line of general purpose cores called SRX is available for evaluation. All cores are stable, silicon proven, clean slate designs in System Verilog, fully compatible with major EDA flows. Most of them have been licensed a few times and taped out at customers who have already deployed this course in the field. In addition to course, we provide all the expected collateral for the CPU IP, like documentation, tests, verification, and synthesis environment. Secondly, we provide specialization and one-stop customization services. We can analyze target application and customize our IP to match specific needs, which allows to achieve significant performance and power efficiency improvements. I'll talk about this later today. Of course, we do provide auxiliary services such as integration into SOC, software migration support, fully featured software development suite, and so on. This is how our baseline of course looks like at the moment. There are 8 cores available, 5 microcontroller class, and 3 application cores. We call them baseline cores, as all our IP is extensible and customizable. And of course, we are working on further designs. So let's start with SR1, which is my favorite one. Here is architecture of SR1 core. SR1 is a compact MCU class core for deeply embedded applications. The design is pretty simple. It works under RISC-V 32-bit instruction set, I or E integer basis, and multiply, divide, and compressed extensions as an option. SR1 works in machine privilege mode only. It is highly configurable and efficient in area. It takes about 10 kilogates in some configurations. It is possible to configure SR1 to include interrupt controller, fully featured debug controller with support for breakpoints in ROM. The best thing about SR1 is that it is open and free, and even unrestricted commercial use is allowed, like modifications, tape out, and so on. Also, it is worth to mentioning that SR1 core comes with full collateral, including SDKs, documentation, examples, software stack, and we even provide free and commercial support. Another thing is that the core and its collateral are good for educational purposes, and we use it extensively in our computer architecture courses. And also, we already have given several SR1 workshops around the world for some universities. SR1 is available through GitHub. There you could find all source files, simulation environment, and extensive documentation. SR1 code is written in System Verilog. Currently, it is around 10,000 lines, so it's pretty compact. The design itself is highly configurable. It includes some predefined configuration to start with, and in case you wish to work with low-level architecture, there are more than 30 configurable options, which makes it also a good platform for studying RISC-V ISA and CPU microarchitecture. Each passing year, RISC-V Foundation is ratifying more extensions, and we try to keep up with these updates. To maintain these new requirements, we provide simulation environment and support for considerable amount of tests. We also benefit from our RISC-V member friends like Imperas, so that we can verify on more tests like RISC-V compliance test suite. By the way, last week we just updated support for compliant test suite. So many thanks to Imperas for excellent work. It is very simple to run our design and simulation. Everything that you need is in the box. We provide test benches, scripts for easy start for all major simulator tools like NCSim, VCS, ModuleSim, and VeriLater. Apart from RISC-V compliance, the open source version also supports RISC-V ISA tests, different benchmarks, and some other sample apps. We don't only provide the core, but also fully featured SDKs, which you could find in a separate SR1 SDK repo. Our approach for SDK is that we use standard off-the-shelf FPGA boards for different vendors, including low-cost options. For this, we provide both pre-built images for a quick start and fully open designs for experiments. Moreover, full software stack is included for every SDK with first stage bootloader, the FirTOS, including BSP, as well as some tests and software samples. You can find user guides under SR1 SDK repo on how to do quick starts. So if we talk about our commercial designs, the first of them is SweRV. This is a high-performance MCU class core with privilege levels and fully featured MPU support, which can be configured as both 32 and 64-bit instance. It also has more feature-rich memory subsystem, including support for the caches and TCM with the cache line error correction. It supports standard interfaces and has many other configurable options. It can be deployed in multi-core configuration, including heterogeneous ones with other cores. We believe it is one of the high performance microcontroller core with RISC-V ISA available today. You can see the numbers on the slide. And the core has been licensed and taped out by the customers several times. The next core is SweRV, also MCU class core, which adds high performance floating point unit. The floating point unit is fully IEEE standard compliant, and it can be configured both for single and double precision operations. The core also taped out several times. The next one is SR5 core. This is our entry-level core for full Linux support, also 32 or 64-bit. It supports multi-core configurations, both SMP and heterogeneous with memory coherency hardware atomics up to 4 cores. The privilege modes are supported, 3 privilege modes are supported there, machine, supervisor, and user. SR5 has a full MMU with virtual memory support, and it is capable to run both Linux or FreeBSD operating systems. The design can be clocked above 1 gigahertz in the 28 nanometer node. And SR7 is our initial out-of-order design. It is currently produced as efficient two-way architecture, but basic core template is flexible, and we are working on other derivative designs based on it. SR7 can be deployed in multi-core configurations up to 8 cores currently, both SMP and heterogeneous, and we are working to extend that to 16. We think it has competitive characteristics, and we are one of the few companies in the ecosystem who can ship such designs at the moment. Here are some examples of the software development kits we provide. There is number of standard FPGA boards we support. The FPGA design is open. It means that you can add features to the system even for the evaluation stage. The software package includes bootloader, choice of the operating system with BSP for board peripherals, and of course some sample apps, tests, benchmarks, and so on. All the cores come with integrated software development tools. The tool chain is based on Eclipse and GCC, and support both Linux and Windows operating systems for the host, and bare metal and Linux application as a target. For JTAG connectivity, both number of low-cost cables and commercial vendor solution are supported. And here are some examples for commercial software vendors which currently support our course: Lauterbach, Seger, ER Systems, and we are working with others to add to this list. Last but not least, we provide customization service. For us, this is the most interesting part, because it is what RISC-V is about, and this has been our long-term continuous focus. All our IP and infrastructure are designed to allow that, and we are especially interested in such projects. Here is how it works on a very high level. Based on the analysis of the target application, we add little extra hardware. This increases area of the chip somewhat, but also allows to complete the task much faster, bringing significant up to orders of magnitude improvements in performance and power efficiency. All this while still staying programmable, which allows nice feature like post-silicon firmware updates and so on. We can do that as a one-stop service, including workload analysis, ISA design, corresponding RTL modifications, and full support in compilers and tools. We have number of very interesting customer projects in that area, including here in Israel. We strongly believe extensibility and customization support is one of the most important features of RISC-V. It would take a presentation on it to go into full details. So instead, here are some basics to give an idea what can be done. Most of architectural and microarchitectural features can be customized, including but not limited to new computational capabilities, extended storage, custom I/O ports, and special system behavior. And this can be deployed in many application domains, from computationally intensive algorithms and signal processing to high throughput applications and artificial intelligence. Here is one of the examples we did for a prospective customer. In this case, we've designed custom extension for SweRV to run a whole bunch of ciphers. Here are the results. By adding little hardware after analysis, under 4% of the CPU cluster level, we've been able to accelerate workload from 60 to more than 500 times, depending on the algorithm. And it was compared to the highly optimized implementation based on the general purpose code. When normalized per megahertz, this is up to 30 times faster than the latest generation Intel i7 CPU. Again, highly optimized software implementation. Besides the raw speed up, I think this case illustrates that often, if your application is fixed, you can go with a much smaller specialized core and save a lot of area and power. Of course, the approach is not universal, and that cannot be done for any workload, but in many cases, especially in the embedded domain, this technique can be used. So, how to get access? SR1 is very straightforward. You can simply go to our GitHub pages and everything is there. You can also always contact us through GitHub or at sr1@syntacore.com. For other cores, access to the full collateral is available after simple evaluation agreement. Contact us at evaluation@syntacore.com for any further questions in that context. And also, you can contact our representative here in Israel, Zahar, from Red Tree Solutions. To summarize, our company offers high-quality RISC-V CPU IP, including open source ones. Our cores are silicon proven and already shipping in volume. And in addition, we offer turnkey customization services based on our IP, and we would be happy to become your RISC-V partner. So, thank you.
Yes, Kate, so there's been a couple of questions come in. I'll just quickly change this over to Larry as I'm speaking. There was a question here on the SCR1, the open source core, on the tool chains that's available. Is there an open source tool chain, and does that support the Windows OS?
Toolchain is open source and it supports Windows.
That's a good one. And then I think you mentioned you have customers in Israel. And also, do you have chips based on your IP?
Majority of the initial wave customers, at least in our experience, build silicons for themselves to use it as part of their product. Most of them are startups. Still recently, there are some which intend to sell it to a wider public in Asia, and currently available designs are mostly MCU class.
Okay, that sounds very good. So I think I've managed to transfer it over to Larry now. So let's move ahead on the schedule. We'll come back to some more questions at the end, Kate. So thank you for that presentation.
There we go.
Yeah, perfect.
Okay, so I should be sharing my screen and unmuted here.
Yes, wonderful.
Thank you. With all due respect to Kate and Zvonimir, I'm going to call design verification the most important task for RISC-V. So with design verification for RISC-V, we've got two new issues in verification of SoCs. One, of course, is the verification of the processor, and the second is the verification of the interface between the processor and the NOC or system bus. These are relatively new verification issues that were not required for ARM or MIPS or other conventional processor-based SoCs. So obviously, if you are building your own RISC-V processor implementation, you need to do DV. If you were using an open source core, you need to do DV. But even if using commercial cores and adding on custom extensions, custom instructions, then you need to do DV on those modifications. And just as a reference point here, ARM runs somewhere around 10 to the 15th simulation cycles per core for DV. So that's equivalent to about 10,000 simulators running constantly for 1 year. And that's in addition to the formal verification work that they're doing, the hardware-software co-verification work with hardware emulators and things. So there's still work to be done with RISC-V processor IP. Certainly, we can use some of the existing verification tools for DV, but potentially some new tools, some new models, new flows are needed. A reference model of the processor is key. Test generation is another key area, and instruction functional coverage is a third area. So before getting into this, let me just provide a bit of background on Imperas. We develop virtual platform-based software development, debug, and test tools, and also processor models and other tools for processor DV and analysis. We do have a background in processors and DV before getting into the software side with Imperas. Simon Davidman, the founder and CEO of Imperas, was also one of the founders of Co-Design Automation, who brought us System Verilog, and before that, a number of other EDA companies. For my part, I was VP of worldwide sales at Veracity, and so to some degree, you can blame the spread of SpecMan, not SpecMan itself. The few people that invented that, and that wasn't me. But certainly I've been in the verification world before, and Kevin, who's been moderating today, has about 20 years of experience combined with ARM and MIPS. Imperas is a self-funded company. We're based in England, in the Oxford area, not Cambridge, and we're about 15 people. What we've been seeing for use cases with our customers, first, processor model development, including analysis and optimization of custom instructions, processor and SoC verification, software development, debug and test, and architecture exploration. And the components that we bring to bear on this are the open virtual platforms models of the RISC-V processors, the OVP virtual platform based, the virtual platforms of the RISC-V based SoCs, custom instruction methodology and tools, the processor verification solutions, and the software debug and test tools. Today, though, we're going to focus on the verification solutions, the reference model, the test generation, and the instruction functional coverage. Just as an introduction here from what experience do we have with RISC-V? We've got a number of customers that are using Imperas for RISC-V DV and a number of partners. In Israel, this includes Mellanox, both for their own internal use and also for the GenPro project. There are other companies around the world, Nagravision in Switzerland, EM Micro in the US, companies in Japan, such as NSI Texi, and there's also a Japanese government project called Trazio, which actually will be talked about some more at the RISC-V Global Forum in early September. And then in addition to the customers, we're working with various organizations, including RISC-V International, where we're part of the Compliance Working Group, the Open Hardware Group, and CHIPS Alliance, where we're part of the Verification Working Groups. We have a direct relationship with Google with their instruction stream generator, with Valtrix, and also with Andes and Sci-Fi for their processor IP and how we model those. Going into a little bit more depth on DV and RISC-V, we see a number of challenges. Staying current with a specification is one of those, because there are changes, especially say something like the bit manipulation instructions or the vector instructions, where those change, maybe not quite on a weekly basis, but regularly. There are also issues with interpretation of the specification. The vector instructions are an issue because these are complex, as complex as the rest of the ISA combined. Asynchronous events are difficult to verify the behavior of the processor. The privilege modes, including debug mode, multi-core, multi-hard implementations, including heterogeneous processing subsystems. The use case there, for example, would be a AI subsystem where you might have both a scalar and a vector RISC-V processor in the same processing subsystem, and then an array of those. And you need to verify not only the scalar processor, not only the vector processor, but the two of them working together. There are also custom instructions that need verifying, but once you add those, you also need to re-verify the underlying processor. There's compliance testing needs to be done. Using the automated test generators is not a trivial task. Measuring test completeness and quality, and instruction functional coverage. So there are a number of DV challenges that we need to address here. So let's go and start with the processor reference model. Actually, as of a couple of months ago, there were more than 100 different RISC-V processor implementations available. So that's certainly gone up. In our experience, every RISC-V processor is really a custom processor. There are implementations, specific pieces of the RISC-V specification, and then adding custom instructions, custom registers, and all the other microarchitectural freedoms the RISC-V allows. At Imperas, we've built more than 10 different RISC-V processor models for our customers and partners. And this is counting all the Andes and the Sci-Fi models as just one for each vendor, because they're implementation specific or microarchitectural choices are essentially the same through their product lines. So the I don't know, 10 to 20 different Andes, 10 to 20 different Sci-Fi processors that we support, those are just one. So we've actually done probably another 10 to 12 RISC-V processors on top of that. Every one of these is custom. We have a documented and proven methodology for adding custom features. We've also made one of our models, basic model, RISC-V OVP sim, made it available for free. This is the reference simulator used by the RISC-V Compliance Test Suite. We use a test-driven development methodology to build our processor models. And our experience with RISC-V and somewhere around 10 other ISAs like ARM and MIPS and Renesas and various others, plus this TDD methodology results in the highest quality processor models. And that's not just a empty marketing boast. Actually, there's a paper that talks about the reference models a bit that is being presented, I believe, today at the Design Automation Conference. With open virtual platforms, we have a library of high-performance processor models. On the RISC-V side, we support 32 and 64-bit instruction sets, IMA, FD, CE, V, and B, plus the privilege modes. We added the vector and bit manipulation instructions as soon as those stabilized. We also support the Andes cores, including their vector instructions, and the Sci5 cores. Custom instructions are easily added by the user or by Imperas when we do have a service for that, but we do have a well-documented process for users to do it themselves. We also have timing estimation tools that can be used to analyze the custom instructions. There's a video for this. These models are open source. They're distributed under the Apache 2.0 open source license. And also all the models have both C and System C native interfaces. I mentioned RISC-V OVP SIM. RISC-V OVP SIM is free. It's available on GitHub as part of the RISC-V compliance test suite. It implements the full RISC-V specification, the full envelope there. It is kept up to date for specification changes, works out of the box with full tracing and debug. Again, there's a video to show you how to use it. On the custom instruction side, we do have this flow. One of the things that we see with custom instructions is that these are driven by optimizing performance for a given domain of applications. So in a conventional processor, you would worry about improving the pipeline to improve performance. And certainly that's done by the RISC-V processor IP vendors like Syntacore, like Western Digital with SweRV. But also what we see are that people are trying to do domain-specific processors and optimize a specific application or set of applications. And so we've developed this flow where the first thing is to get a baseline to characterize the existing application with the standard instruction set. Then there are the new instructions developed that are added to the application, added to the model, added to the timing estimation capability. And then we go and characterize the new instructions in the application and iterate on that process. From there, we can optimize and document the model, do things like instruction coverage, line coverage, and then release and deploy the model. So these are different things just about the reference model. But now moving on to the other two pieces for design verification, the test generation and instruction functional coverage. I'll talk a bit about compliance testing, directed tests, the constrained random test generators, methodology, step and compare, and then instruction functional coverage. So compliance is not verification. It seems obvious to say that, but that's not always a given with people. But it's still quite valuable from a DV perspective to run the compliance test suite. So compliance is different. It's looking at the architecture, not the microarchitecture. Compliance is about the ISA specification and not the detailed implementation. But with compliance checking, one of the key things is, have you read and understood the specification? And this can be a key thing, because as much as we have worked on the specification within the RISC-V International working groups, there are still ambiguities there. And we still, every time somebody runs the compliance test, there's usually a question about one thing or another. At Imperas, with our test-driven development of the processor models, we've developed test suites We have a vector compliance test suite, a directed test suite that is in use by 2 customers with 2 different vector configurations. We also have a compliance test generator. So we have automated generation of compliance tests, which currently achieves greater than 97% coverage of the specification. We have the directed vector tests, and we also have mutation testing capability. So mutation testing is essentially inserting a bug in the design and then seeing whether that bug can be is visible using the test suite that you have and the outputs of the test. So this is actually a key quality metric, especially for directed tests, and in particular for trace and signature comparison flows. So our mutation testing actually runs quite fast. When we are looking at our directed test compliance tests and the others, we're running about 1 billion mutated tests per compliance suite in less than 1 hour total runtime. With constrained random test generation, so this is something that we've been using within the community. There are several instruction stream generators available as open source within the community. The most popular is from Google. We've worked with Google to enhance the methodology, to use RISC-V OVP SIM as the reference model, and to add functional coverage. We've also worked with Valtrix. They're a commercial company based in India. They have a test generator themselves. This also uses RISC-V OVP SIM as the reference model. From a methodology perspective, one of the things that we've seen going back to our verification experience and working with others in the community is that the trace and signature comparison flows are inefficient, and in some cases insufficient for complex processor DV. So this methodology works for compliance testing, which uses a signature comparison flow, but it is difficult or impossible to test with asynchronous events. So with exceptions and interrupts on things, it's very difficult to use this flow. And so we've built a system Verilog encapsulation of our RISC-V reference models to use in a step and compare methodology. And this supports single or multi-heart processors. It supports any combination of features, including custom instructions, and it can be just a single processor or a processing subsystem. So let's look a little bit more at the flows available here. This is the Google open source instruction stream generator. This gets the instructions it generates get compiled up, resulting in an ELF file. The ELF file is loaded onto both the RTL and the Imperas reference model. There's a signature log that's created, and then there's a comparison that's done. There are functional coverage capabilities with the Google instruction stream generator now. We've actually added functional coverage for the vector instructions and the bit manipulation instructions. With this methodology, we've actually worked with the Cadence, Mentor, Synopsys, and Metrics RTL simulators. The Imperas contribution to this is the model and the simulation golden reference for the RISC-V CPU. And we're also working to extend this flow to support a step and compare DV methodology in addition to this trace compare. Valtrix has a slightly different methodology here with their Sting tool, but again, they're using RISC-V OVP SIM, and what they're doing is essentially combining these reference test results in with the tests so that they create a self-checking set of tests. with the step and compare methodology, this looks a little bit different. There's a test suite here that gets compiled up, and test suite gets loaded onto the RTL memory and also the reference model memory. And what we've done is a system Verilog encapsulation of the Open Virtual Platforms model. And this system Verilog encapsulation uses the system Verilog DPI API. And what this allows is for the system Verilog test bench to do the control, to do the step and compare for the DV. Actually, you can also use SpecMan, not just a system Verilog test bench, with this methodology. So the advantages of this methodology are that the tests are going to stop immediately upon failure, so you're not wasting simulation cycles. Also, there is no stored log file, so the test log data is dynamic. You don't have to worry about large log files. And this supports indeterminate and asynchronous events. So while this is a step and compare, this doesn't mean that these are running in lockstep. Actually, because there are indeterminate events or asynchronous events, the RTL can be stepped before the reference model so that the reference model then knows what it is supposed to do. As we put this together, this shows a step and compare DV example. Here we're using the Cadence Excellium system Verilog simulation. This is the Imperas RISC-V reference model simulation. And actually what we've done here is we've got things running with both. It's a true co-verification environment so that you can set breakpoints on either side of this if you want to stop and examine where you are in the simulation. This is especially valuable for asynchronous events and to investigate compare failures. I mentioned instruction functional coverage. So this is just system Verilog functional coverage focused on the instructions, and we've added that in to our environment. And in particular, we've added functional coverage into RISC-V OVP-SIM. The reference model for compliance now has functional coverage added into it. I didn't mention this before, but I will say it's not a scientific survey, but as far as we're aware, everyone that is developing a RISC-V processor seems to be using RISC-V OVP-SIM. In summary, DV is a critical issue for users of RISC-V. There's a need for reference models, for test generation, for DV metrics. And we've got the expertise and experience with this. And for more information, you can go to the Imperas website or the Open Virtual Platforms website or the RISC-V International Compliance GitHub repository. Or you can contact me directly. I'd be happy to answer any questions. Thank you very much.
The question came in for you was, in your DV flow, you highlighted System Verilog. Which tool vendor do you support?
The example that I showed there with the screenshot was the Cadence RTL simulator. But actually, we work with Mentor, we work with Synopsys. We also work with Metrics, which is a startup that is doing cloud-based system Verilog simulation.
Okay. And then the RISC-V models support custom extensions. What language is that? What language is that used?
Are developed in C, and actually we have documentation of the process that is used to add custom instructions, custom registers, full examples, documentation of the APIs. It's a pretty easy process to add in the custom instructions.
Great. Great. Okay, so hopefully that's fair warning. Thank you for your time there, Larry. And I think we'll hand over to Zvonimir now. So Zvonimir, you should have control of the screen. If you can just share your slides, you should be all ready.
All right. Good afternoon, everybody. My name is Zvonimir Bandic. I work as a Senior Director in Invest in Digital Corporation. And I'm also a chair of CHIPS Alliance. And this presentation today will be a short introduction to CHIPS Alliance, and I'll also describe a couple of our open source hardware and software projects. So I'll go through who we are. I'll briefly describe today's compute requirements and challenges brought up by a diversity of devices emerging in the Internet of Things and Edge. And then I'll describe the CHIPS Alliance projects. CHIPS Alliance is an organization which develops and hosts open source hardware code. Think like IP cores or open source CPUs. And also open source software design tools, which is the fastest growing component. We have a number of different software projects targeting hardware development. And we also are hosting interconnect IP, focusing on both physical and logical protocols, which is attracting most interest. It's a barrier-free environment for collaboration that follows the standards organization framework for collaboration, discussion, and development. And in terms of legal framework, follows Apache v2 license for the contributions. Shared resources, which save time and money, are a key reason for CHIPS Alliance, and it allows lowering the cost of hardware development for both IP and for the tools. In terms of the members, we have many companies on the board, many universities. It's actually difficult to fit all the logos, including Open Road University project, which is a collaboration of the number of universities in the United States. Organizational structure of CHIPS Alliance is that we are a project under Linux Foundation. We have a structure that loosely mimics the RISC-V International. They have a board of directors with myself, with Richard Ho from Google, Jeanine Key from Alibaba, Dave Ditzel from Esperanto, Yusuf Lee from Sci5, David Kellett from Intel, and Professor Borivoje Nikolic from UC Berkeley. The technical committee monitors the progress in different groups and is composed of work group chairs and is chaired by Henry Cook from Sci5. Ted Marina is currently an interim director of the organization. We are actively recruiting for an executive director, and we are in the final process of making an offer to a director who will be announced most likely in August or early September. We have significant help from Linux Foundation that provides a program manager, Brian Warner, and a variety of legal and finance services. The outreach committee chair is Michael Gilda from NMicro. He's been active in organizing a number of in-person events. Well, we could do that before March this year, and then many meetups and other events post-March and post-COVID. So today's compute requirements and challenges are getting wider and wider. The emergence of consumer and industrial IoT has led to a broad set of requirements across a broad set of processing and connectivity profiles, a number of different devices, and increased variety of workloads. This has significantly impacted development costs and difficulty of entering different markets, especially IoT. So the key challenges that we see are cost of hardware is increasing significantly, especially with the traditional approach of reducing the cost by going to high resolution lithography nodes, which cannot be cost effective unless there is enough volume. and volume is only possible if the unification of workloads and use cases is possible. Innovation is often stalled in corporate structures, and a need has emerged for more and more purpose-built architectures. So what are the goals and deliverables of CHIPS Alliance to address these challenges? Number one, lower the cost of development by leveraging common IP, such as RISC-V cores, neural network accelerator IPs, Encore components, interconnects, etc. And then number two, develop open source software design tools, which enables new level of innovation where design engineers can actually modify design tools themselves, which becomes very interesting, especially for the physical design. And open source collaboration can now benefit hardware as well. Designing open source RTL, enabling purpose-built solutions is one of the primary goals. In addition to building a new business model development and promotion of open source policies. So the example of that is a Western Digital partnership with CodaSIP, which has enabled a new business model on top of SweRV cores that are maintained in the CHIPS Alliance. And CodaSIP actually provides a services on top of these open source cores. We had multiple events organized starting last year. We had a first workshop in Mountain View on Google campus in June 2019. We had a design verification workshop in Munich in November, and Chisel and CHIPS Alliance workshop in Lapides on January 29, when Chisel, a work group, joined CHIPS Alliance. We had a big plan for the China workshop that we had to cancel due to COVID. But instead, we had many meetups and attended many online events such as this one today. All right, so in terms of the projects and work groups in CHIPS Alliance, the largest work group is a Chisel work group, has over 35 active developers working on a new toolchain for RTL design. Interconnect work group contains multiple projects, most notably AIB PHY, which is a specification for the chiplets interface from donated from Intel. Then a TIE-Link cache coherence and bus protocol that came from Berkeley, and it's in active use in many RISC-V designs. And finally, OmniExtend, which is a export of the TIE-Link over Ethernet, and I'll talk about it more later, but it enables symmetric multiprocessing with RISC-V systems. There is a Rocket SoC generator work group, which is another project that came from Berkeley. There is a cores work group that focused on the line of embedded SweRV cores. It currently has SweRV cores that came as a donation from Western Digital, but is anticipated to have more cores from other companies in the future. And finally, software tools work group that currently has a very active Verilator project where we are extending Verilator support for System Verilog. There's a Fuse SoC tool support for SweRV cores. And there's a CocoTB, which is a Python-based design verification flow that now supports a Verilator for simulation. So Chisel is a very interesting innovation that came from Berkeley and has been very popularized by Sci5 and several other companies, especially in China. And it allows for designing SoCs in a high-level language, Scala, that has a very similar flow as Java, and in its backend, it has a tool called Fertile that actually allow exportation of either files for simulation on the tools like Verilator or FPGA bit streams, or actually full ASIC design. So it's beginning to look very similar, like a standard software stack in Linux. There's a new website for Chisel. And in January, we announced a new home for Chisel project in Chips Alliance. SweRV core roadmap is a project that came into Chips Alliance from Western Digital. It has two generations of cores, SweRV EH1 and SweRV EH2 and EL2. SweRV EH1 is a 32-bit 9-stage superscalar dual-issue core developed targeting 28 nanometer TSMC, capable of running at 800 megahertz in a worst corner, and with an area of 0.11 millimeters squared. And this core has been deployed in several Western Digital flash controllers. The second generation of cores is upgraded SweRV EH1 core, which now targets 16 nanometer TSMC, can run up to 1.2 gigahertz, and most notably is multi-threaded and allows even better performance to power profile, especially for workloads that have a lot of exits on a system bus. Finally, there's also a SweRV EL2, which is a small 4-stage core, single issue. And this one is really targeting the many of the micro-coded finite state machines that you will typically have in any kind of large system SoC. The I think donation that came from Google is they're a very popular open source stressful transaction instruction generator. Google has worked actively on this project together with Imperas and Metrics, and it allows a systematic testing of the RISC-V cores, and it can be done in the cloud. And that's probably the biggest advantage of this contribution. And we have several member companies in Chips Alliance actively using this flow. The Esperanto company contributed Dromaio, which is their RISC-V 64-bit emulator for cost simulation. And most notable capability of Dromaio is that it's reasonably fast. It achieves about 17 MIPS on a 3 GHz Intel Xeon. Verilator is a project that has, in the last several months, attracted a lot of interest in the Chips Alliance. Number one feature of Verilator is that it's super fast. Depending on configuration settings on a Verilator, it can achieve performance that's often 10 times faster than the commercial tools. And it supports Verilog and subset of system Verilog, but not the full system Verilog. And what we wanted to do is really advance Verilator to the point where it's not just used for a specific test of the RISC-V CPU cores, but also to actually enable full system Verilog simulations, so that full universal verification methodology toolchain can be established on top of Verilator. And the goal obviously being that you can create open source design verification environments which would enable better sharing of verification IPs between partners. So this project is happening in a tools workgroup in Chips Alliance, has many active contributors from Western Digital and Micro, Google, and is making very nice progress. And we believe by the third quarter of 2021, we will have full system Verilog supported. Fuse SoC tool is a famous tool, package manager that came from Olaf Kingren, and it's now supporting SweRV cores. And in general, it allows very efficient design of the SoCs, and and it allows exportation of either simulation files for Verilator or bitstream files for the several supported Xilinx FPGA boards, as well as Quartus and Icarus. It's now used in a number of open source projects that I'm aware of. We are using it in the OpenTitan project in the low risk, and it's also used in Western Digital for commercial applications. Open Road project is a very exciting contribution that came from a number of universities in the United States, led by Professor Andrew Kang from UCSD. It has an amazing aim to create a no human in the loop digital hardware compiler capable of advanced node tapeouts. It's basically a digital integrated circuits RTL to GDS flow, single click flow. And Open Road Focus is really the ultimate ease of use and runtime, but it's a great platform also for open source developing of the future features of the flow. So this is tool that has rapidly matured in the last couple of years, and already has several silicon proven designs behind itself. And it has been adopted in a number of projects, including the open source PDK project that Google has been spearheading and recently announced on one of the FOSSI events. The Open Road capabilities, as I mentioned, are really that you're starting from the Verilog, and with a single operator click, you can go from synthesis to floor planning, place and route, and GDS2 file generation. And if you're using the open source PDKs that came from a Google Skywater collaboration, you can have an open source GDS2 files as well. And for the end of July this year, we are targeting release of the version 1.0. Finally, Intel has been addressing a very important and interesting problem in a number of the chips ecosystem, where it's not cost effective to do the complete integration of the SoC on a single piece of silicon die. This is especially important for the cost and power optimization, where certain Encore components can be produced in older lithography nodes, and performance critical components can be produced in the latest and highest density lithography nodes. And also in the use cases where people want to integrate very different technologies. For example, if you want to integrate a MEMS component with a advanced silicon node component, or if you want to integrate advanced silicon nodes with a optical interconnects. So this is basically the motivation behind AIB. So this is a scalable chiplet die-to-die physical interface. It's optimized for low power and high bandwidth. And it's built on top of protocols like AXI. So you basically export your buses on the chiplets interface. And we have been actively working on a roadmap to AIB 2.0, which has actually been announced in a press release this week. OmniExtend is another interconnect interface that we have been working on. It's meant to be a memory fabric for the open source memory fabric. It's sort of targeting RISC-V community, because RISC-V community is very open and many companies are already using tiling, but actually it can apply to other architectures equally well. What it does is it takes a tiling cache coherence messages and packages them on top of level 2 Ethernet package, and therefore allows usage of the standard Ethernet switches, such as Barefoot Tofino from Intel or Broadcom switch, and the cache coherence protocol messages that come from one core in a system can actually travel using normal Ethernet PHYs, Ethernet cables, and Ethernet switches, and can find its memory locations on the other RISC-V nodes. So this architecture is attractive because it enables several interesting use cases. Use case number one is building symmetric multiprocessing systems, like traditional NUMA. The second use case are different use cases for building memory appliances that can be added to the cluster, or building a computational storage elements. So there's a little demo here that that we have shown last year on the RISC-V Summit. We put together two RISC-V nodes implemented on FPGA boards. Each one had 4 hearts or 4 RISC-V threads, and they were connected to the Ethernet switch. And we have been able to boot Linux on one of the nodes, and even though that specific node had 4 threads, after the boot, when you go to the proc CPU info page, you would actually see all these 8 RISC-V threads, 4 from the local node and 4 from the other node connected to a switch. And that's my last page. Thank you very much for your attention, and I'm a few minutes ahead, so I'll be happy to answer any questions.
Great, thank you, Zvonimir. We certainly appreciate your scheduled timekeeping today. Just one question. I was going to offer you a chance here. You used a phrase earlier in your presentation, which I don't think you fully explained, and it may not be familiar to everybody. What is Uncore?
Encore is I've heard the word Encore for the first time maybe like 5 years ago from Professor Krste Asanovic at UC Berkeley. It basically indicates all the components on the SoC or CPU that are not CPU processing elements. So Encore, and a great Encore example is if you look at, say, AMD recent announcements for their CPU packages. They have disaggregated their CPU x86 CPU cores, which they're producing on some very advanced TSMC node. Don't ask me which one, but they announced it. Right. And then their Encore is actually on a separate die, and it's probably produced in a different technology node to optimize for power. And it provides a network on the chip, level 3 cache, PCI Express, root complex, and sort of any other not core component. And then these are packaged together into your multi-die package. So that's so Encore really indicates everything that's not the core. And with some of these chiplet technologies, you can even imagine Encore components gravitating on a separate chiplet.
Great. Thanks. I think that was useful just to explain that. So what I'm going to try and do now, if I can just wake up and get everyone back together again, we can open this up to everybody. Right, so for all the panelists, if you can now, let's see if I can just do this.
Should I stop sharing now?
Yes, so you stop sharing, Zvonimir,
right.
And then if all the panelists can unmute and put your videos back on. And I can see that there's been quite a few questions coming in here while we've been talking, so I'll try and go through these. So let me just start off here at the beginning. Obviously here in the Meetup, normally we do all these things very personably one-on-one, and that is the great chance to actually meet some of these experts and pose the questions to them that you've been burning to ask. So I'd just like to start you off here. I'd just like to go through this one-on-one. If you could all share your personal reasons why, RISC-V is a great momentum. Everyone's really excited about it. There's a lot of activities. There's a lot of stuff in the media. But just on a personal note, what attracts you about RISC-V and why are you involved? And I'd just like to go through that question, each of you in turn. And so perhaps with Kate, if we could start with you, your personal view on RISC-V, and then Larry, and then Zvonimir.
Okay, so I think the best thing of the RISC-V is its customization. So there are several bases and several extensions that can be added, and we actively use all of them. And also there is there is a place for any custom extensions, and so I think that is the greater thing in it.
Okay, great.
And everybody can be an architect. So yeah.
Yes, I mean that's a fair comment. Now everyone can play with processor design. It gives a lot of freedoms. So let's see if we can go to Larry. Larry, why are you involved with RISC-V?
That's a good question, Kevin. It made me stop and think, why am I involved here? I've been fortunate to have participated in some leading edge technology previously, for example, with Veracity and in the verification space, and with other companies as well. But one of the unique things about RISC-V is the community that is being built here. So it's not a single company that is advancing a technology, but a community that is advancing a technology and an ecosystem to support that. And so I find this a new and refreshing and exciting approach to technology development, and I'm excited to be a part of it.
Great. Well, thanks for sharing there. So Zvonimir, why are you involved with RISC-V? What's your view on the world?
So the key reason why I got involved in RISC-V is an idea that ecosystem can be developed where a very large number of companies can produce RISC-V processors and SoCs, especially for the sort of larger computing machines, for the high performance computing, data center, edge, etc. The attractiveness to the open source instruction set chiefly came from the idea that if there are multiple manufacturers of the CPUs, the interfaces can become more open. And I actually, before I entered the world of the CPUs, my primary interest was building memories and storage, and it's still my primary interest in my day job. Is producing a low latency storage devices and very high capacity memory devices. Those devices tend to prefer a direct CPU interface. And when you have a lot of open source designs, and when you have a lot of manufacturers that have a freedom to build their own designs any which way they want in terms of combining open and closed source IP, this vision becomes much easier, and promoting open source interfaces becomes much easier. So for me, it was really that kind of peripheral part, the freedom to customize encore pieces of the CPUs and SoCs.
Looks like you're having fun with all this freedom as well.
Absolutely, yeah. And then it really took, then RISC-V Investment Digital really took a life of its own. I think other people became interested in having embedded cores. Other people got interested in reaching a certain level of IP freedom and independence to sort of put together a system, especially when low power was a requirement. So then things kind of branched out.
Okay, so I'd like to now turn to one of the questions that came in while you were all talking. So this question is really about automotive. So I'm just going to read the question here. So with automotive, there's a lot around functional safety, software test libraries, and lockstep. Clearly, automotive is a big, exciting industry. There's a lot of innovation that's happening there right now. And so you would think that RISC-V would be attracted to these new opportunities. And I'd just like to see if the panel could share their views on addressing functional safety with RISC-V.
So I can start on that. We've at Imperas, we've been working with automotive customers for, well, actually our first customer ever was in the automotive space was Audi. And so we've been working in this space for a long time. With RISC-V specifically, I think there's some really exciting opportunities, especially in ADAS and automated vehicles, where the capability to design custom things with RISC-V is quite exciting. From a functional safety perspective, you need to test and test and test some more to make sure that you've got things right from the safety perspective. And with the virtual platform-based environment for software testing, with the processor models for verification of the actual hardware, I think we're in a nice position to help in the automotive market with RISC-V.
Okay, thanks, Larry. Zvonimir and Kate, any activities with automotive? I guess with Zvonimir, that's probably a little bit far away from your world.
No, I'm in Western Digital, definitely very actively participates in automotive market because of our variety of package flash solutions that are growing in importance in automotive market, especially as cars begin collecting more and more data as we are transitioning to different ADAS 2 and then ADAS 3 and systems getting eventually towards fully self-driving cars. So yes, we actually we are not currently shipping RISC-V based flash controllers into those markets, but stay put. I expect that will probably happen. We also have in this specific area of this specific question, we have a collaboration with Dr. Timothy Jones from Cambridge. He has actually been doing active research on the sort of parallel execution for reliability, and I believe he has been using SweRV H1 core in his research.
Okay, great, thank you.
Okay, so we do feel interested in that space, and we are doing something in that area, but it is internal roadmap, and I cannot comment on the availability.
Yes, I think that's true of a lot of this IP, is that sometimes your customers don't let you talk too openly about their activities, but it sounds like you're doing well. Just looking here, maybe just one of these more general questions. RISC-V is an open ISA, and a lot of people have associated that with the open source momentum and movement. So in the software world, open source has been a tremendous factor, and there's many statistics about the number of Linux machines that are running around the world and serving probably all the internet that we're using here today for this talk. Open source in the hardware domain has struggled somewhat to get some traction, but obviously with Chips Alliance now, open hardware, there's some real industry backers coming into open source. And the presenters today both mentioned open source hardware IP as a key part of their talk. So maybe you could just all share a few views on your take on the hardware side of open source.
Mm-hmm. I think that there is a big problem with open source hardware, is that most of these projects created but not supported by its creators. So one of the best things of SR1, as I think, is that we accept that it is open source and that it is high quality. We also provide maintenance and support for it, best effort support, and also commercial support is available for someone who is interested.
Okay.
From the Imperas perspective, we're trying to walk an interesting line with open source models and commercial tools. And in the open source hardware area, it's been difficult because the cost of developing IP, cost of supporting that IP has been significant. And so whether it's on the ecosystem side with the EDA tools or on the IP side, just the sheer costs involved have been difficult to overcome. With RISC-V, with the large community that has come together around RISC-V, we're seeing, I think, critical mass for open source hardware, at least in terms of open source designs. It will be interesting to see how this plays out, because still we're at the early days of in the RISC-V community of seeing these open hardware projects actually get to silicon and actually be used by real systems. So it's still not clear that this is going to be the path forward for RISC-V, or that it's going to be a fully open environment, but it certainly seems encouraging right now.
Yeah, I think maybe there's few minutes left. From my perspective, the key value that comes from the open source hardware is a collaboration platform and a collaboration opportunity. The open source hardware under Apache v2 doesn't just doesn't mean it's free. It's probably not free, because any kind of hardware that's going to be integrated into a system will require significant investment in terms of design verification. That thinking of it as free is probably wrong. But the fact that you can start working with partners without necessarily entering into NDA agreements immediately, and the fact that open source hardware allows you to work with multiple partners at the same time is a very attractive idea. And I fully agree with Ekaterina in terms of providing a support on open source hardware. That's a key. So what we've been working on in CHIPS Alliance is doing exactly that, making sure that the major open source hardware components or future open source software tools actually have a backing company that is willing to provide a commercial 24/7 support, while committing obviously to keeping the IP in the open source domain. So that's the key for SweRV cores. And we have very similar plans for the Verilator simulator, where there will be one company or multiple companies that will actually be providing commercial support.
Great, thanks for mentioning support. That was where I started my early stage of my career. So I was on the receiving end of some of those phone calls with people close to tape out and needing some help there. So I've got another question here, which is one of these more general ones. Obviously, RISC-V has got a great capability, but as people look towards the whole system modeling environment, virtual platforms, obviously that's probably more in our area, but in general, as people are looking at RISC-V to solve new and creative approaches to these bigger problems, do you think this is also now a chance to look at system level modeling as well?
Well, certainly it is. There's a chance to do that, but maybe going back to the earlier part of the question, one of the interesting things about RISC-V is the different capabilities that it has the ability to sort of mix and match. And so in some of the areas we've seen, I mentioned this a bit in the talk, in AI, for example, you might have an innovative approach to AI, which involves an array of processing elements where the processing element includes a scalar processor and a vector processor coupled together. And so I think RISC-V offers the opportunity to take a new look at innovative SoC architectures and to make some of these array of processor architectures that have been discussed for 20 or more years to make those a reality now. So there's an opportunity to rethink SoC and therefore system architecture with RISC-V.
Okay, well, I appreciate everyone's time here today. It looks like we're just a little bit, few minutes over the time here. So I think I've addressed all the questions. If not, I do apologize if we didn't get to your particular question. We can certainly I'll review this and we can come back to you more directly afterwards. So I think with that, I think I'd like to just wrap up here this evening. Say thank you to my panelists. Thank you very much. Appreciate your faces on video. You all look very happy and well rested. So appreciate you joining. And of course, the viewers, thank you for joining this webinar today. As I say, I apologize, it's not in person. The Meetup style, I think, is great, where we can actually talk and share these experiences one-on-one. So hopefully in the not too distant future, we'll all be back together again. And then just to thank you for your attention today. And as I mentioned at the beginning, there are a couple of events coming up in September at the Global Forum, and then out towards December, the RISC-V Summit will be coming up. And hopefully we can see you join those events also. So with that, I'd just like to say thank you to everyone to participate, and hope to see you all again soon next time.
Yeah, thank you very much, everyone.
Thank you.
Thank you very much.